Well, how much work is done if an object is moved from one position to another and then returned to the original position? And you probably guessed that if we're in a inserted vector field, the answer would be no work at all. Does it seem logical? Well, by the way, don't forget, you can't stop and then return. So if you move from one place to another and return, that's what it means. Does it seem logical that since work is force times distance moved, that if the distance moved is 0, then whatever the force is, we got 0. So we need one more definition to make sense of the next theorem. A closed curve, a curve C given by a vector valued function r of t equals some, x of ti plus y of tj plus maybe z of tk. And if that, and the t value going from a to b, and it's closed if r of a equals r of b. In other words, if it winds up starting out where it finishes. Oh, wait a minute. Yeah, starting out, maybe I should better say it like this. If it winds up stopping where it started, there we go, r of a equals r of b. It starts at r of a, ends at r of b, and they are equal to each other. Equal in the vector sense. The I, j, and k coordinates are all equal. So can you see that means that it starts and ends at the same place? Can you see that the line integral of continuous conservative vector field will be 0 on all closed curves that start and stop in the same place? So, theorem 15.7. Let f of x, y, z be some function m times I plus some function n times j plus some function p times k, m, n, and p, all functions of x, y, and z. And let that have continuous first partial derivatives in an open connected region R. Remember, connected, right? And let C be a piecewise smooth curve. Maybe I should say in R instead of on R. But then the following are equivalent. F is conservative, that is, F is some del F for some potential function F. 2. The line integral f dot dr over curve C is independent of path. In other words, it doesn't matter how you get there. And 3. The line integral is 0 for every closed curve. These all mean the same thing. So it's conservative. In other words, it's the vector field for some potential function f, and the line integral is independent of path, and the line integral is 0 for every closed curve. That means it starts and ends at the same space. And think what that means. If you evaluate the potential function f at the beginning and at the end, you're going to get the same thing. It starts and ends at the same place. So perhaps a simpler curve can be obtained for the line integral in example 2, since any path between 0, 0, and 8, 4 will work. Well, remember how complicated that guy was up there? Where was he? Here, remember? Oh, we got 896 over 3. How horrible that was, right? And when we did it this way, it was even more horrible. I didn't even bother to do it. I just let my software take care of it and give me a numerical answer. And I let my software take care of this and give me a numerical answer. That wasn't too awful bad, but there are paths that would have been nicer than that. So, perhaps any path between 0, 0 and 8, 4 will work. And the answer is, yeah, any path will give you the same result. So evaluate the line integral over a simpler path in parts A and B above. Recall, one path was this one, and we got a horrible integral. One path was t cubed I plus t squared j, right? Neither one was nice. How about if we just took, the path 2ti plus tj? Remember, this line we're looking at had slope 1/2. Remember, it went to the point between the point 0, 0 and 8, 4. So let's just use the line segment that connects the point 0, 0 and the point x equals 8, y equals 4. And for t going from 0 to 4, that is the same path. And then the line integral is, remember this was our function we were finding the line integral of. And so we just say, okay, well, a simpler path would be this one. X is 2t, so 2t squared, that's x squared. Y is t, so t squared, times the derivative of x would be 2. And then 2xy dy, well, there's the 2. X is this, y is this. Dy, derivative of t, is 1. And so I won't bother to evaluate it, but you know, it wouldn't be all that bad to evaluate something like this from 0 to 4. Because the numbers are going to be nice. This is just strictly a polynomial. I guess we get 4t squared plus t squared, so that's 5t squared times 2 is 10t squared. And then here's another 4t squared, so 14t squared. So that would be 14t cubed over 3. And t cubed would be, when we put in 0, of course we get 0, so 4 cubed would be 64. 64 times 14, I'm going to guess that's 896 over 3. So not nearly as ugly as either of the integrations before. As a matter of fact, I just did the integration in my head. How about that?
Nice work.
Thank you.